Chapter is dedicated for the electrical characteristic of bipolar transistors. Since we have enough time to discuss about this chapter, we're going to discuss about the bipolar transistors in more detail than we have done for MOS. Okay, let me just review the difference between bipolar and MOS transistors. Can I get a little bit more? Okay, here we go. Transconductance is usually higher in bipolar than that in MOS transistors, and we're going to discuss about this a little bit later. More complex fabrication in general, we're going to talk about this a little bit later. Lower input impedance, since bipolar are current controlled device. Well, MOS is it's not really current control. It's a voltage control because we apply the voltage between the gate and the substrate, the MOS, metal oxide the semiconductor capacitor, right? But in bipolar transistors, we actually let the current flow from the emitter to the collector. So we're going to discuss the details on this electrical properties of a bipolar in the next sections, and higher current capability in bipolar. So in bipolar transistors are usually used for the protection circuits for input and output because it has a capability to endure high current. And generally faster switching times because it deals with the high current, and generally more complex device physics. Well, it's MOS is a unipolar, but in a bipolar it is electrons and holes are both involved in the operation. So naturally it has a more complex device physics and larger physical size than MOS. So in a modern VLSI or ULSI, nobody is using the bipolar transistors for the integration. Most of the integration is done on the MOS transistor because it's simply the bipolar is larger than the MOS transistor. How large? In a linear scale, it's about 7 times bigger than bipolar transistors, I mean. So if you talk about the area, the size of that, maybe it reaches to the 50 times or something. All right, so let me just turn off this a little bit, and let me discuss about the bipolar transistors. It look like this, okay? And source and drain. So we are talking about the IDS, the current between drain and source, controlled by the gate voltage. That is MOS transistors. And usually we are going to talk about the electron or hole. So the MOS transistor is actually unipolar transistor. On the other hand, bipolar transistors, its configuration is going to look like this, okay? It usually takes the junction isolation. So this is the emitter, and this is the base. This is the collector. That is the bipolar configuration. And here, in the lateral schematic drawing of this is we have an emitter, base, collector, and then we apply the voltage here to control the current between the emitter and the collector, and then we apply say the voltage between the emitter and the collector like this. So basically what it does is we are going to inject the electrons or holes to the base, and we make the base as thin as possible so that these electrons can survive, can be collected in the collector. And that current is going to be controlled by the bias between the emitter and base. That's what it is, right? So all the characteristic or comparison that we have talked about in the first of this class, which has given and the 7, 1, 2, 3, 4, 5, 6, 7, those comparisons all come from the physical configuration of these two transistors. Okay? And in terms of the fabrication, the main feature is in the MOS transistor, the length here is important. We call the gate length. Gate length. That is the key parameter for the fabrication technology levels. Okay, how small we can make. That is the key things in fabrication for the fabrication engineers. Now in bipolar, this base width is the key parameter. Okay, for the bipolar transistors, and we're going to talk about why the base width is important in bipolar transistors in a minute. Okay, but as far as the fabrication is concerned, the MOS transistors, the gate length is important, and bipolar transistors, this base width is important. And this gate length should be controlled by, gate length has to be controlled by lithography. Okay. It's mainly controlled by the lithography and etching technologies. Etching technologies. On the other hand, for the bipolar transistors, the base width has to be controlled by the diffusion process. Okay, so this part, the MOS part, we have lots of things to do in terms of the equipment and fabrication technology and so forth. For example, the lithography, it is related to the lens focusing and the exposure automation, all those things, that has to be related to the MS fabrication, and that will determine the integration levels. On the other hand, for the bipolar transistors, there's nothing much we can do about this diffusion process. Okay? So, even though we had an idea that the transistors can be made in the MOS configuration, in the industry, the bipolar transistor has appeared in the market first. We can easily make the bipolar transistors compared to the MOS transistors. For example, for MOS transistors, we have to maintain the cleanness. That is the key issue in the MOS transistors. Bipolar transistors, the cleanness is not that important. We can work in the air, for example, in the bipolar transistors. Why MOS transistor, the cleanness is important? Because we have to have a capacitor. If you look into the cross-section of this, we are going to metal, that is the gate, and oxide, that is the gate oxide, and the semiconductor, that is the substrate. Okay, that is basically the capacitor. It works. The main principle is a voltage control, we can say. Okay, here the current is actually important. So if electron is going to inject it to the base, it just means that we have injection of hose from the base to the emitter with the same voltage. So naturally, we have to compare in this bipolar transistor the current on the emitter and current to the base. We have to compare this. And obviously, we want to make this thing as big as possible compared to the base current. And in the modern technology, we can make it 1,000 times bigger. So we may say the IB, the base current, is trivial. It's almost normal. Okay. Anyway, so the MOS transistor appeared in the market about in the 1960s. Engineers had to learn why the cleanness is important and how clean we should make to workable MOS transistors and so forth. Bipolar transistors, it just industrialized in the early 1950s. Okay? But as has been summarized in the text, the MOS has a great advantage over bipolar transistors in terms of the electrical characteristic and the fabrication terms. I mean, the MOS can be much, much smaller than the bipolar transistor, so it is beneficial for the integration circuits. So it takes places of bipolar transistors, MOS transistors. So first, bipolar transistor has appeared in the market, and then we had a PMOS in the market, and then we had an MOS in the market, and then we have a BiMOS. We call this a BiMOS. Bipolar and MOS at the same time on the same chip. And then we just have a NMOS, and then we have a complementary MOS. Things like this. It has been changed. I should say, now we have CMOS and MMOS at the same time. Okay. And I told you that the transistor idea has been, I has been established in the MOS transistors, but the industry has to make the bipolar first ahead of MOS because of the technology difficulties. When we overcome the industrial barriers for the MOS fabrication, then obviously people want to make MOS first before PMOS, because the electrons are moving much faster than the holes. But it turned out that we had to do something more to make MOS than PMOS. So PMOS appeared in the market first, and that is related to the threshold voltage control. And then people come to know how we can make controllable threshold voltages in MOS. And then PMOS, nobody likes the PMOS because MOS is much faster than the PMOS. So every indicator circuit has been made by the MOS. But, and to summarize in the text, the protection circuits has to be made with a bipolar because MOS it cannot carry high currents. Okay, it cannot put up with high voltages. So the input circuits has to be made with a bipolar. So bipolar and MOS have been fabricated in the same substrate, and we call that the BIMOS. But with the advent of technologies in the MOS, now we can make protection circuits with the MOS as well. So these days, nobody's working on the bipolar, you can say, okay? There's almost pretty much summarized the bipolar, comparison of the bipolar and MOS. Okay, let's turn on. Okay. Well, we are not going to have a class on the Wednesday, right? You know that? Do you know why we don't have a class on Oh.
Yeah, already planned vacation.
Mm-hmm. Okay. So this is a cross-section of typical bipolar transistors, and it has a buried layer N plus and N as a collector, P, and N plus as an emitter. Okay, this is a typical number for the doping level. And if you do Sims profile of the dopants, then the substrate has a constant doping level, and then the buried layer, the concentration of the dopants for the buried layer is going to go like this, right? And then you are going to grow epitaxial layer on top of this, so that actually this part has been out diffused from the buried layer. Means this buried layer, you just implant the antimony, for example, for the buried layer, and then you grow epitaxial layer on top of this, and this epitaxial layer thickness reaches to 10 micron or so. And during that epitaxial growth, you are going to have out diffusion of the dopants to the epi layer so that you are going to have some profile of the dopants towards the epitaxial layer, so something like this. It looks almost symmetrical, isn't it? And then in this epitaxial layer, you're going to have collector dopant, and this collector is going to be going to put into the epi layer during the epitaxial growth. So when you grow the epitaxial layer of a silicon on top of the substrate, you're not going to make a pure silicon. You just put some phosphorus or arsenic or something like that to make this thing N minus. Okay, and that is the epitaxial layer collector concentration of the dopants. You usually use the phosphorus, and you usually use the antimony for the buried layer, and there is a reason for that. For the antimony, it has a low vapor pressure, and it has a low diffusion coefficient, so that the out diffusion can be minimized if you use the antimony. Well, the antimony and arsenic has almost the same diffusion coefficient, but arsenic has a very low vapor pressure, a high vapor pressure, so that it vaporizes at low temperature. That's a problem. So the arsenic cannot be used for this buried layer, because during the epitaxial growth, usually the temperature for the epitaxial layer is about 1100 degrees centigrade. It's a pretty high temperature, very slow process to maintain the texture, the single crystal. You have to grow the single crystal for the epitaxial layer. So at high temperature, at low deposition rate, so that the out diffusion is very important, and also the vapor pressure is also important. So arsenic and antimony have the same diffusion coefficient for the out diffusion, but antimony is preferred because antimony has a low vapor pressure than the arsenic, so that it's basically it is not going to be vaporized during the epitaxial growth. Anyway, and then you have to add some of the phosphorus during the epitaxial growth to make this thing, epitaxial layer, the M minus, the substrate. And you have to use the phosphorus for that, because you are not going to put a huge amount of dopants. We have to make this thing N minus, not N plus. Okay? So the phosphorus is the best thing for that, for this M minus layer. And then the base layer, it should be P type, and then we don't have any choice for the P. We have to use a boron for that. We don't have any choice. So we have to use the boron for the P, and for the emitter N plus, we have to use the arsenic for this. Okay? Because the arsenic has low diffusion coefficient, so that the junction depth cannot be big. We need a shallow junction for the emitters. So we have to use the arsenic, and we have a choice for the phosphorus for that, but you have seen in the early chapters of our class that if you use the phosphorus for the M plus, and then we have an emitter push, okay, vacancy generation underneath the emitter, so that this boron is going to be diffused a little bit farther than is expected from the Gaussian profile. And that is called the emitter push, right? And then that emitter push will make the WB, the base width, a little bit bigger, wider, longer than we expected, so that the device function is not going to be good for the device electrical properties of the device, right? So there is we don't have much choices for each layers. Buried layer antimony and the collector dopants should be phosphorus, and then the emitter at the base should be boron, and the emitter I should have arsenic. Okay, there is a reason for that. So that is the seems profile that we are going to have for the dopants in the bipolar transistors. Okay, that pretty much covers the fabrication of bipolar transistors. Now, the basic operation, let's derive the basic relations for the electrons flowing from the emitter to the collector. That is the main thing, right? That is the main thing, and the current between emitter and collector, the electrons and holes are both involved in this current, so that we call this transistor bipolar transistors. On the other hand, in the MOS transistors, only electrons or holes are going to be involved in the drain current. So MOS transistors is going to be called unipolar transistors, and then we can distinguish NMOS or PMOS depending on the free carriers. In the bipolars, we don't call that N bipolar, P bipolar, things like that, because electrons and holes are both involved in these transistors. Okay, so the important thing is to understand the basic operation of a transistor. The important thing is the derivation of electrons from emitter to the collector, right? So we start by assuming the device current gain is high, so that the base current is 0. In other words, in the configuration that I showed, emitter, base, collector, and then the electrons is going to flow from the emitter to the base, across the base into the collector, with the voltages between emitter and base, right? And that voltage not only moving the force the electrons flow from the emitter to the base, at the same time it is going to force the holes moving from the base to the emitter with the same polarity of the voltages between the emitter and base. So we just assume that holes movement from the base to the emitter, that's negligible. Okay? We have to think about this later, but it turned out that it is a very good assumption, because most of the modern MOS bipolar transistors, it has a pretty high gain, which means this current level is 1,000 of the emitter current. So it is not that bad assumptions. So we can assume that the base current is 0. The current of a whole current is 0, and then that whole current consists of two terms. One is from the electric field between the emitter and base, and then the other is the flux from the fixed second law, fixed first law. Okay, concentration gradient give rise to a current. So it consists of two terms, and those two terms should equal to 0, because the total whole current from the base to the emitter is going to be 0. So we can deduce the electric field established in between the emitter and base with this equation, with this assumption, and that turned out to be something like this. Okay? And we just assume that in the base we have a uniform concentration, but in reality, in the base, it cannot be, the boron concentration cannot be uniform on the base, because we are going to do that by implantation, and we expect to have Gaussian profile in the base. So we have some concentration gradient, of course, and this concentration gradient, by the way, will give rise to the electric field, which is not going to be zero. And then it turned out that the direction of this electric field, which comes from the concentration gradient inside the base, will help the electron hole current. Okay? So this is basically going to aid the whole electron current from the emitter to the base. So it's not going to make worse of our discussions, the logic of our discussions. Anyway, so this is the electric field existing between the emitter and base, and then electron flow to the emitter to the collector is going to be the same equation that we had before. Now this time we are going to talk about the electrons, so that the sign is reversed from the first equation. And of course, the electron current from the emitter to the base, it consists of the drift current. The electric field, you have to notice here, the electric field is the same electric field that we have derived here for the holes, because that electric field existing in the emitter and the base. Okay? And then, of course, the diffusion current from the Fick's first law, the concentration gradient of electrons in the emitter and the base is huge, because the emitter is implanted to the N plus, and the base is a p-type, so that the electron is a minority carrier in the p, so that the concentration gradient across the emitter and base is going to be huge. So it consists of there's two terms, and then this electric field, we substitute the electric field that we have derived here to this electric field to get the electron flow between the emitter and the base. So this is the equation for the electrons to flow from the emitter to the base. Okay? And if you look at that carefully, you can rearrange that. If you don't know how to arrange this thing, you have to ask your brothers, which is in high school. Okay? And then this is going to be rearranged to this. And then with the drawing, we have a space charge regions, and the dimensions we are talking about, the base width xb should be not the physical distance between these junctions, but it should be on this xb. You have to eliminate the space charge region width, so that the net distance that we are going to talk about in the base is going to be xb here, from here to here, not from here to here. Okay? And you put those configurations in the equation, then neglecting depletion regions, the effective base width xb is metallurgical base width or whatever. And then this is going to be equal to this equation, and you can see the integration of the derivative is going to be returned to the Pn product. So this integration is going to equal to this part. Is a simple mathematics. And then we know in the diode characteristic, the Pn product at XB, this is the physical position, the location. And then Pn product of x equal to 0 is going to look like this. This is the Vt, is the thermal voltage. And then we put this thing into this equation, and then we end up with this equation. Okay? We end up with this equation. The Jn, the current, electron current from the emitter to the base, is equal to some values here, which has been divided by the integration of 0 to xb on this p dx over dn, that is a diffusion coefficient. And if the diffusion coefficient is constant, then it can come out from the integration, and then you end up with the boron concentration integration of a boron profile in the base region. Okay? That is the total amount of a boron in the base, simply. Okay? So the QB is, we said the QB is equal to QA, that is a cross-section area, and from x equal to 0 to xb, P, the boron concentration, and the dx. Make an integration of that, and that should be equal to the total charge in the undepleted base region. That's interesting, isn't it? And then the current, we can see that some value we call the saturation current, and then modulated by the base collector voltage and base emitter voltage there. Okay, and then this saturation current is going to be equal to this number here. And then the QB is the total charges of boron in the base. It's simply you have a total charges. So if this immediately you can see that if you put a very lightly doped base, you should dope the base very lightly to get the high value of the saturation current, and that high value of saturation current is directly related to the high current of electron to the base. We want to make this ion as big as possible. Okay? This is an extremely important result. That is the basic electrical characteristic of the bipolar transistors. Note, usually only one of two exponential terms in here. One of these terms is negatively has a negative here, the reverse bias, so that one of these two terms should be negligible. So usually only one of two exponential terms is important because of the fact that one junction is typically reverse biased. When the device is in saturation, both junctions are forward biased, and both terms must be included. This is the exceptions. But usually one of the junctions is going to be reverse biased, so that in this equation, the ion is controlled by one of these two terms. The quantity the QB, the total charge in the base, is called the Gumbel number. When you want to make it as small as possible. It is the total integrated base charge, and since the current is inversely proportional to the charges in the base, it is important to minimize the base current, base charges. So IC transistors use low doping levels in the base. Okay, and it can be done if the base is uniformly doped and the electric field across the emitter and the base in the base is zero, and out of the analysis of the short base bias told us that we go like this in the short base diode case. In a long emitter or long diode, we have this exponential decay of the minority carriers, but if it is a short diode, we have a linear decrease of the minority carriers. Okay, NP means in p-type the electrons, which is the minority carriers, and then we have these whole values from the diode analysis, and then we know the doping level is different, so that the minority carriers in the base is much higher than in the emitter. And if the base doping level is constant, so that we can say the charges in the base is a simply geometric multiplication of the area and the XB, which is the volume, and then Na is the concentration, so that just a simple multiplication of the geometries, and then we can say the current, electron currents from the emitter to the base is somewhat something like this. This is a basic collector is a reverse bias, okay? Reverse bias, so that it's almost 1. And then this can be written alternatively, something like this. And then this is the important features of the bipolar transistors. Okay. Now you can see they're almost a straight line. This is the emitter current, and this is the base emitter forward bias voltages. And then this exponentially is linear, and then that is the real characteristic of the bipolar transistors. We have a tremendous amount of a current from the emitter to the base, and that electrons is not going to be recombined in the base by making the base very, very short and doping level very low. We have a huge amount of current coming from the emitter to the base, and then is successfully reached to the collector. Then we have a tremendous amount of current. Okay, that is the amplification action of the bipolar transistors. Okay, this Wednesday we are not going to have a class, and then next Monday, a week from now, we're going to talk about the bipolar device scaling thing, but maybe I'm going to prepare some of the detailed operation principles of bipolar transistors in between. So maybe on Monday we're going to talk about the electrical characteristics of a bipolar transistors before the bipolar device scaling. All right? And I'm going to provide you the handouts on Monday.